So that being the case, that's the usual focus. That's what you're paid for. So what then is the point in talking about studying unsolvability? It seems sort of counterproductive, doesn't it? Well, the two main, according to Sipser, there are the symbol, mathematical symbol. There are two main reasons for studying unsolvability. Well, one is it's useful. It's actually useful to know, because if you learn that a particular problem you're starting to work on is in fact provably unsolvable, then you're going to have to change tactic, right? You're going to have to either just abandon the whole enterprise, or modify, simplify, change somehow your problem into a form, into a modified, simplified version of the problem that is solvable. Okay? And knowing about unsolvability, and particularly knowing that the problem you started with is in fact provably unsolvable, that forces you to change your tactic, change your strategy. Right? You just have to, because if you don't, you're just going to waste your time, because it's unsolvable. Right? You'll never solve it in its current form, because it's mathematically provably unsolvable. Okay, so that motivates you then. If you're going to keep working on the problem, you have to change. You have to modify the problem and convert it somehow into a problem that is solvable, by simplifying it and modifying it somehow. Okay, so knowing about unsolvability is useful, right? It can. So if you know about unsolvability, you may look at a problem and say, let's see, from my experience in studying unsolvability, maybe this problem is unsolvable. So you check it out. But if you knew nothing, if the very idea of a problem being unsolvable never entered your head, then you may waste huge amounts of time trying to solve something, and it's just not solvable. Right? So it pays to know. You can save yourself a lot of wasted effort. Okay? So it's useful. So that's reason A. And the other one is more sort of a cultural reason. Now, Sipser's, my main criticism is he's not clear in many ways. I mean, I love his general structure. I find the whole course very well structured. Admire him for that. But my main criticism of him is that quite often he's not clear. Like, for example, here, cultural. What does that mean? Does that mean like cultural as in cultural anthropology, study of cultures? Or does it mean culture as in, he's a very cultured gentleman, sophisticated, suave, very knowledgeable, and so on? Well, it's the second. It's part of your general culture to know such things. So even if you're dealing with solvable problems all the time, which is what most computer science people do, of course, then but knowing that some problems are unsolvable, then that gives you a sort of deeper perspective, a broader understanding of computability in general. Once you know that there are limits, then it makes you look on what is solvable differently, because perhaps makes you question, there may be what's the threshold between solvable and unsolvable, and how can you convert, for example, an unsolvable problem into a solvable. So it's part of one's computer scientist's general knowledge. It just a well-cultured computer scientist, if you like, should know that there's a whole category of problems that are just provably unsolvable. Okay, and just the sheer interest. I mean, you can put other reasons. Just it's interesting, right? That's one I'd add. Right now, the next you can probably see the first line in the next session. So this is sort of a bit of a summary of previous chapter, a lot of important concepts raised, learned, and sort of lead into sort of motivator, if you like, what we're going to talk about for the rest of this board. Now, the first section, so chapter 4, section 1, there are, how many sections? Only two. There are only 2 sections in this chapter. So the first one is on decidable languages, and the second one is the halting problem, the famous halting problem. So, well, you can probably just guess. A language that is decidable, what does that mean? Well, we've done this kind of thing before. A language is said to be decidable if there is some Turing machine that decides it. Okay? Now, because now we sort of don't distinguish between a Turing machine and an algorithm, the Turing machine is the algorithm, so to speak. So a language is decidable if there's an algorithm that decides it. And what does that mean in turn? Well, we've done that also. A language is a Turing machine, or an algorithm, decides a language if each string that belongs to that language. Remember, a language is just a set of strings. It's a simple definition of what a language is. So each string that belongs to that language is recognized, is accepted by the algorithm, by the Turing machine. Same thing. Okay? Each string in the language is accepted by the algorithm, by the Turing machine. And any other string that is not a member of the language, it's not a member of that set, that string is rejected. So, in other words, for all strings, this algorithm, the Turing machine, the Turing algorithm, either accepts the string or rejects the string. That's it. There's no looping, right? The machine is a decider. Remember, deciding, or a decider is a Turing machine that decides, meaning it always halts. It never loops. It does not go into a situation where the Turing machine just keeps processing forever, indefinitely. Okay? It may take a long time, but it'll eventually halt. It'll always halt on any string, and the outcome, the decision, if you like, because this machine is a decider, the outcome is either it accepts the string or it rejects the string. That's it. There are only two possibilities. Okay, so if the language that consists of all those strings, and if all of them are accepted by the machine, by the algorithm, then that language is said to be decidable. Okay, that's a bit of revision from last chapter and earlier. Okay, so and this board and next we will be talking quite a lot about decidable languages. In fact, I'm jumping ahead a little bit here, but we will translate. We will translate problems into a language format. We will take a problem and represent it in the form of a problem about a language. And why? Well, we'll do that next session.